All right, guys, I think we're certainly a quorum at this point, so I'm going to go ahead and get started. Sorry about Monday, but when you feel terrible, and lecturing when you feel terrible is terrible. So I just scrubbed it, and here we are. And what that means is we will just be missing the last lecture, so there's not really late in the quarter an easy way to make that up. It's possible. We'll see how our invited speakers go. So we've got today's lecture, and then we've got 2 weeks of kind of outside speakers talking on things that are a little bit closer to sort of research and clinical projects. And I guess what I'd like you to be thinking about in the background is finishing up your assignments. You'll have the lab tonight, or the lab assignment due, a week from now, week and a half, I forget what the due dates are. And you'll get a new homework assignment. We delayed that a little bit too because it felt like things were kind of piling up a little bit. And so we'll give that out on Monday. But while the lectures at the end, they're still important for material that you won't have a homework assignment on because it's late in the quarter. That material is still important for the final exam. And so coming to lecture is still going to be important. And they're also the clinical speakers, the last 2 speakers in particular. I think you'll finally get some more sort of hands-on, direct ideas about how MR is used clinically. So those are routinely really interesting and kind of fun lectures and that. And I still try to pull some questions from that material as well. So anyway, keep that in mind. If there's time at the end of the sort of invited 4 lectures, I may provide some kind of review material or something like that. But one thing I'll point out is at the beginning of each of my lectures, I try to provide a summary of the previous lecture. And that's probably really obvious material to focus on. Like, you should have a pretty good grasp of that. And you might have to back up a few slides to sort of get, sort of the background you need to understand, a certain expression, a certain relationship, a certain sort of conclusion. But those are pretty good ways of knowing what I think is important for the class. So keep that in mind. For tonight, we've got the lab, again, from 6 to 9. The 6 o'clock group, you guys know where to show up. Get there close to 6. We'll start as soon as we can. We're going to do the same thing as last time. We'll give you an hour to work on the lab, and there's not really much in terms of pre-lab. The assignments on the lab assignment is online right now, so you can download that, and you should read it and look at it beforehand, so you sort of anticipate what you're going to be doing as a group. If for some reason you can't get it or can't access it, just let me know. I post things, and I just sort of assume it works. Anyway, so have a look at that. I'm guessing that the first group will finish before 7:30. I'm only going to give you guys an hour, just kind of in fairness, right? So probably you'll finish before 7:30, which means that this group 2 groups, if you get there a little bit early, we might be able to start you a little bit early, and I'm sure you'd rather go home a little bit early than stay a little bit late. So I can't make any promises, but if you get there closer, like 7:15 or something like that, or even 7:15 is probably good, then we might be able to start just a little bit early. So keep that in mind. These are the groups that we plan to use, and we have 2 groups on 1.5T and 3 groups at 3T. So the 1.5T groups are sort of competing against each other, and the 3T groups are competing against each other. You'll see what this looks like. Today's lecture is actually really directly related to the lab tonight. We're going to talk a lot about artifacts. And what you're going to have in the lab tonight is everything will be set up. There'll be a phantom that's in the scanner, landmark, and sort of there's a protocol to use. And you're going to have the freedom to make lots of adjustments to that protocol, and you'll want to do so because the first images you'll get with the existing protocol will be terrible, okay? And so your job, there's a scoring system, but your job is to try to make the best image that you can within the hour that you're allotted. So you'll have to be changing all of the various imaging parameters that we've been learning about. It's a gradient echo sequence, but you'll be able to change, flip angles and resolutions and bandwidth and just pretty much anything you want to. And your job, again, is to make sort of a diagnostic quality image. And you'll get scored on different sort of measures of image quality to figure out sort of who's the winner, right? It's a pretty fun lab. People usually kind of get into this. And Patrick has spent quite a bit of time making a good phantom for you guys. So that should keep it interesting. So at any rate, this is the plan. If there's no objections, then we'll scoot right along. If you have a conflict or a problem, just grab me right at the end of class. But maybe just by show of hand, does anyone have a conflict with what's posted? Okay, cool. Okay, so where are we in the class? This is the kind of material that we were talking about at the end of the last lecture. And we talked about, there was a lot of procedural steps to sort of get to this point, but we ended up with this Fourier reconstruction formula. And this formula is important to us because it tells us how we can use the acquired data. This is the K-space data here, how we can use the actual acquired data to actually invert, so to speak, this information to recover the image of the underlying object. And there's a bunch of terms in here, and we should remember what these terms look like. But fundamentally, we have some series coefficients that are related to sort of the magnitude of the points, the different points in K-space. We have what we call the Fourier step size, which is related to sort of our pixel resolution. We introduced the idea of having a window weight so that we could actually we can multiply, and I'll show you this in just a second, but we could multiply a window across K-space to filter it a little bit, and that could consequently improve our image quality a little bit. And then we have these hopefully now familiar spatial frequency encoding terms. And really all this expression says, in a perhaps slightly complicated way, is that we just have to add up all of the appropriate spatial frequency terms weighted by the appropriate coefficients and maybe some windowing term. And if we add all of those things up, then we can recover the image of the underlying object. And this is also effectively what the discrete Fourier transform does. So we write this just in very shorthand by saying we just can do a fast Fourier transform. This idea of applying the windowing function was introduced because for some imaging data, for example, when we have really high contrast boundaries, so here the outside of this phantom object here is really, really bright, and it has high contrast relative to the background, that will give rise to Gibbs ringing. And you can see the Gibbs ringing in sort of this sort of bright again, dark again banding artifact, if you will, that sort of goes up and down. You also see it in the left-right direction here. And somewhat remarkably, just by dot multiplication, so every pixel location in our window function is multiplied onto the according pixel location of our K-space data. And just doing so-called dot multiplication gives us a new sort of K-space array, if you will. And the Fourier transform of that recovers an image that looks a lot more reasonable to us and perhaps a lot more even diagnostic. The cost of this, though, was not free. And it showed up when we talked about the Fourier pixel size. So we could characterize the Fourier pixel size by the full width half max, or some measure of what we call the point spread function. And for Fourier imaging, what we've mostly been talking about for this whole class, the full width half max is just characterized by 1 over big N delta K. What's 1 over delta K? Field of view, right? And so this expression can just be written a different way, which is the field of view, which is a dimensional measure, it's centimeters usually, right? Divided by the number of encoding points or pixels, right? And so this gives a very natural definition for spatial resolution, right? How big was your field of view and how many points did you discretize it by? Was it 10 points or was it 128 points or was it 512 points? And so this gave rise to the definition of what we call the Fourier pixel size. Then we saw that the Fourier pixel size, or the full width half max of the point spread function, when we introduce the idea of a windowed reconstruction, gets to be bigger. And so the downside, so to speak, of doing this windowed reconstruction here is that the spatial resolution of this image here is going to be slightly lower. The full width half max is going to be larger. But it seems like a reasonable penalty when you look at the improvement in the overall image quality. So windowed reconstructions are very widely used, but they do have the downside of slightly decreasing your overall spatial resolution. We also saw this in another way, which is if we look at sort of all of these representative lines, the dashed lines and solid lines representing phase encode steps that we might use in an imaging experiment. If we do the 2D Fourier transform of just the data within the sort of the gray lines area, we'll recover an image of our underlying object, but it won't be a very high resolution image because we haven't gone out very far in K-space, so to speak. And so we know that acquiring fewer high phase encode lines decreases our overall resolution. And if we add lines to our acquisition and we go out farther and farther in K-space, we recover a sharper image of our underlying object. But importantly, notice that the delta K between these two, right? So the step size between acquiring this line and acquiring this line and acquiring the next line, those are constant, and it's constant even when we're getting higher resolution images. So delta K is fixed. So you can get a full field of view image with just 2 lines, say. It'll just be a very low resolution image of that object. And ideally, we want to encompass not only the entire field of view, but we want to do so with pretty high or at least adequate spatial resolution. So we have to get the number of K lines that accord with the spatial resolution. you saw this in your homework problem, and this is just another example of the same. Again, we can have fully sampled Fourier space and take the 2D Fourier transform of it and recover the underlying image of our object. And if we pull out the odd lines, this has the effect of increasing our delta K, right? So the step between, say, this line and the next line has gone up by, say, a factor of 2. And as a consequence, when we take the fast Fourier transform, we'll end up with an aliased image of the same underlying object. And so this, of course, is not preferred for research purposes or diagnostically. And so we need to make sure that on the scanner, we prescribe the appropriate field of view so that the scanner designates the appropriate delta K, and we get an acceptable field of view coverage for the underlying object. And so we know that if we uniformly skip lines in K-space, the result will be an aliasing artifact. And what we're going to talk about for a fair bit today is various different artifacts. We'll start by talking about noise. Noise is an artifact. We've already talked about some artifacts, and I'll kind of review a few of those rather quickly. And then we'll dig into a couple artifacts a little bit more specifically, and then we'll talk quickly about a handful of others. MR is, I suppose, like any imaging modality, has innumerable kinds of artifacts, and it becomes important if you're a diagnostic radiologist or a researcher that you can identify artifacts. And in fact, it was just happening with one of my grad students' research projects that he couldn't quite figure out what was going on. He was looking at images, trying to figure out what was going on. I said, don't look at the images, look at the Fourier data. You go back to the Fourier data, and oftentimes you'll see something in your Fourier data that's not always obvious how it's going to show up in your image data. So your image data may give you an artifact that you can't quite understand, but the Fourier data may make it very clear. And that, in fact, worked really well for his particular problem. Okay, so believe it or not, we've made it mostly through this diagram. We've talked all the way through this course about how we go from magnetic moments all the way through to forming images. And we've talked some about image reconstruction, that sort of summation equation that we started with today. I'll talk a little bit about image reconstruction today in the context of having multiple coils. Oftentimes we have not just a single coil, but maybe a dozen coils, or even 2 or 3 dozen coils, 100 coils, depending on the exact application. So that's a little bit more to the reconstruction story, but we've largely made it through this. And I think this is a good example of how you want to answer the first question on your final exam. All right, so I'll review that. I'm not sure at what point, but if you go back to the very first lecture, I think it's the very first slide, or maybe it's after the title slide, but it is the first question for your final exam. It's basically, explain to me, how does MRI work? And you've got 2 pages, closed note to figure it out, right? Which hopefully you know a pretty good way of answering that question already, but take some time to practice it because it ends up being maybe 10% of the final exam or something like that. Just a few more comments about the final exam. That first part is closed book. So you'll have as much time as you want, but if you take more than 20 minutes, 15, 20 minutes, you're just eating into the time that you need for the rest of the exam. You'll have 2 pages where you can write your answer explaining to me. I would suggest using these kinds of details and answering that question. How does MRI work? And after you finish those 2 pages and you're satisfied with what you've written, you hand that in, I give you the rest of the exam. The rest of the exam is open note, meaning you can bring any of the materials that I've printed out for you and any of your handwritten notes, but it's not open book. Okay? So you need to be able to rely on any notes that you've made for yourself or any of the handouts from the lectures, but you can't just come up with a stack of books and your iPad and whatever else. Okay? Okay, so one of the artifacts I want to spend some time talking today is noise, right? In a perfect world, we wouldn't have noisy images, and if our imaging technique were sufficient to have, extremely high signal levels, then maybe the noise wouldn't be that important. But MR, it's really sort of magical that it works at all. There's a number of sort of physical parameters that if they were just a little bit different, just really wouldn't work. And the bottom line is that we work in a sort of acceptable signal to noise ratio, meaning that the noise in our images is present, but it's usually not so bad that it's problematic. But depending on exactly what you're doing with your sequence, you could end up in really low signal to noise regimes, and then you have a problem to solve. So noise is a very real problem in MR for sure. So what do we mean by noise? Well, here's just a time series. So it's the same image acquired repeatedly, right? And at every pixel location, there's some fluctuation. There's some underlying reason that the signal intensity is not exactly constant. And so we can talk about different characteristics for the time history of any particular pixel. And so if we look at a pixel that's, say, up here, there's some little pixel right at the end of this arrow tip, then maybe it has an average value that's something like 10 in terms of just signal units. But it also has some fluctuation about that mean. And so at any point in time, when we capture it, we get a value. But we know that were we to image repeatedly, and we don't typically do this, but were we to image repeatedly, we'd have some fluctuation. So we'd have some mean, some variance associated with the signal estimate. And then, of course, we can go to another pixel location. This will be a lower signal-to-noise location. And it's lower in signal-to-noise because the mean signal is, of course, lower. And maybe the variance or the variability in the underlying noise is the same as this top signal. So the signal is lower, the noise is about the same. That's going to be a lower signal-to-noise image. So this is the picture that I want you to have in mind. When it comes to experiments, one of the best things you can do to measure the signal-to-noise is the experiment I'm showing you here. Repeat the acquisition for as many times as you need to get a good sense for the mean and variance within a pixel. There's a few reasons it's important that's one of the best ways to do the experiment, but it really gives you a pixel by pixel estimate of the underlying signal to noise. And so I think it's the most fair way, it's amongst the most fair ways to characterize the true signal to noise. But if acquiring a single image takes you, a minute and a half or 2 minutes, and you need 32 images to get a good signal to noise estimate of every pixel, it all of a sudden became a half hour or an hour long experiment. So it's not always feasible to do it that way. So we'll talk about some shorthand methods for doing this as well. In general, and you saw this in the first lab, what we mean, or at least a way of calculating the signal to noise, is to estimate the signal, which is just the mean signal intensity in some region of interest. This would be a pretty large region of interest because it's probably spanning multiple tissue types, white matter and gray matter, for example. But just as an example, you can draw a box on some region of interest that you care about. And then we can calculate or characterize the noise, and the noise is just characterized by the standard deviation of the background in a region of interest outside of the object. So we want to get to a region that doesn't contain underlying tissues, because the tissues will have a variance because of their tissue properties as well, right? So if we try to calculate the variance in this box here, we'd have multiple sources for the underlying variance, not just the noise, but you'd also have tissue heterogeneity. So you want to get to a region that's outside and ideally artifact-free. And that's one reason it can be challenging to find a good region outside of the head in this case. You may not find a region that's really artifact-free, but as a simple example, this is one way that we calculate. It's probably the simplest way that we calculate the signal to noise. So this method of measuring the SNR, it's widespread. People do it all of the time, but there's a number of reasons that that's imperfect. So especially if you end up working in research, you need to reevaluate how you're estimating the signal to noise rather than using necessarily some simple metrics like this. Okay, so I said some of this already, and in fact you saw some of this for the first lab already, but we typically define the signal to noise as being some signal amplitude or mean signal amplitude divided by the standard deviation of some noise signal. And we know how to get these things from different regions of interest. If we want to, we can talk about the contrast to noise as well, and that just being the mean signal difference between, say, white matter and gray matter, or muscle and fat, or lung and liver, or whatever, divided by the standard deviation of some underlying noise signal. So these are useful and important measures that we can use to characterize the underlying imaging system. And I think you'll need those for you'll need those for this lab tonight as well. All right. What that's all about. My favorite thing to say about our Wi-Fi network here is I shouldn't say it. It's not quite to say. It's not a very good Wi-Fi. I'm being recorded, so be careful. Okay. So let's look at this. So this is image space and k-space, right? Shown adjacent to each other. So left-hand side is image space, right-hand side is k-space. And the only point here is that the Fourier transform of noise is just noise. So there's sort of no big surprise here, perhaps, if you know something about signals and systems. But the bottom line is that the Fourier transform of our noise just gives us back a purely noisy object. So we might expect that our K-space data, if it's corrupted by noise, has some basic K-space values that are the coefficients for the spatial frequencies that represent the underlying object, but it has to be in addition to some underlying spatial frequency coefficients that just give us noise. Fortunately, they're going to be there. And so here's another example of the same, a little bit perhaps more pleasant to look at. Here I'm just changing the signal to noise. Should be fine, yeah. Here we're just changing the signal to noise actually in the K-space data on the right and showing what happens to the underlying image on your left is the image, on the right is the K-space data, obviously. And if the K-space coefficients are overwhelmed by noise, they become very large in amplitude relative to the spatial frequency coefficients, then the image just degrades to becoming a fully noisy image. And obviously our job is to come up with imaging protocols, and you'll be confronted with this tonight in the lab, imaging protocols that allow for, say, acceptable signal to noise, while not allowing your scan time to be too ridiculously long. We'll talk about that trade-off as we get more and more to the signal to noise description here. Okay, so let's talk about noise and how it relates to imaging parameters. So we start off with, we have some K-space data, I'll call it S hat of K. And that's just going to be equal to the S of K that we had to begin with, which accurately represents the underlying object. But we have to add to that some noise. And so we call this epsilon d, or Kc sub d, which is also a function over the K parameter that you're talking about. And so what I mean by this coefficient here, or this parameter here, is that it just represents data noise, meaning that every K point is corrupted by some value. And epsilon is going to be, or this Kc variable is going to be, in principle, some distribution. We'll talk about what its statistics look like in just a second. But you're going to add, you might be adding a negative number, but you're going to be adding something to the actual K-space coefficient that contributes noise to the underlying imaging data. And just for reference, this actually comes from equation 840 in the book. We obviously have an imaging space correlate to this, and so we can talk about I hat, which is going to vary over x, is going to be just the actual underlying image itself, which we assume to be sort of perfect, if you will. But we have to add to that some imaging noise that varies over x as well. And so this is just the image. And this just is the next equation in the book, which is 841. So two simple definitions of how noise gets added to the underlying information and corrupts what we care about. So you'll remember the Fourier reconstruction expression that I showed you on the first review slide of today. It was suggesting or telling us that the image itself can be recovered by the sum of a bunch of coefficients multiplied on spatial frequency terms. So we know that by Fourier reconstruction, with, let's say, the image itself equal to 0. So we're just going to let the image itself be equal to 0. Then what we would recover would be that the Kc sub I for every point, where this here is an index over, that's going to be like pixel location. Space, if you want to. Every pixel has an index, the first, second, third, fourth pixel, if you will. And the noise, if you will, in the imaging space is just coming from that Fourier reconstruction equation when we let I of x be, sorry, it shouldn't be equal to, yeah, it should be equal to 0. That's fine. So then we just recover this sum equation, minus n over 2 to n over 2 minus 1. And here we add in the noise from the data domain, where n here is an index over the Fourier coefficients. And then we need our spatial frequency weighting term, which just looks like e to the I 2 pi, and now we have an m times an n divided by a big N. And so this is just saying, it's the example I gave you before, that the summation of the data domain noise over all the relevant spatial frequencies just gives us image domain noise. And that image domain noise actually has a lot of properties in common with the data domain noise, the k-space noise itself. We'll talk about the similarities between these distributions in just a second. Specifically, because this was the Fourier reconstruction and we were talking about space-limited signals that only exist on the field of view, then this is the expression for minus n over 2 is less than n, is less than n 2. And just for reference, that gets you back to 842 in the book. So this is just saying that if you do the Fourier reconstruction of a bunch of noise, you just recover a bunch of noise. Okay? And it falls out by taking that Fourier reconstruction equation and using the definitions that we had for both the signal data and the image data in the presence of noise. So let's talk a little bit about what the data domain distribution looks like and what the image domain distribution looks like, or what are its properties. And so we can talk about C sub D. And we saw from this first expression that the noise itself is additive. So it's not that it multiplies in or comes in as some exponential function or some other kind of function. It just simply adds in. So that's simple. The noise itself is assumed to be, and it's a pretty good assumption, is assumed to be ergodic. And that means that you get the same average over space or time. So that's immediately related back to the picture I was showing you before, what you did in the first lab and what you'll do in tonight's lab. We draw a region of interest over a background volume, some box that's outside the thing of interest, and we calculate the standard deviation. And we're assuming that the standard deviation within that box is representative of the standard deviation were we to repeat the experiment over time. Okay, and that's what we mean by ergodic. We can average over space, we can average over time, or we can calculate the variance over space or the variance over time, and it has the same statistical properties. It's a reasonably good assumption, but it's imperfect. There are reasons why true imaging systems violate that, but it's okay for today. We assume the noise itself is stationary, not a jaw-dropping assumption, but it just means that the source of noise or the underlying cause of the noise is not something that's moving as a function of time. So it's somehow isolated and fixed to the coordinate system of the object that we're imaging. It's uncorrelated, and this means both over space and time. So there's no sort of history dependence. There's no sort of underlying. It's effectively random, right? Like truly random, Gaussianly distributed random noise. It's also white, meaning this noise characteristic here is white, and that means that it has what's called a constant power spectral density. And that effectively means that the kind of noise that we have is not different for different spatial frequencies. We have the same kind of noise for all spatial frequencies. Somehow I'm running out of space there. What else do we have? In general, it's going to be zero mean. So the noise itself doesn't bias the underlying signal. It doesn't cause the signal to drift up. It doesn't cause the signal to drift down. Just random instantiations of noise will have a total zero mean. And then the last thing we assume on top of all of this is that the noise itself is Gaussian. And it's going to have a specific standard deviation. And that standard deviation we define as sigma d. And we'll need this sigma d when we work through some later expressions. So these are all just different properties that give us some insight as to what are the characteristics of noise that enters into an MR system. Again, they're not perfect assumptions, but they're pretty good assumptions. Okay, so we need to flip over and talk about the other side too, which is what does the image noise look like in the image domain? And it has all the same properties, so I won't write them all, but it's additive, and it carries all the way through. Because it's just a linear transformation between the data domain and the image domain. It just comes through as a sum weighted by a bunch of spatial frequency terms. So it still shares all of those identical properties, except for in the end, we'll make a different definition. We'll say that we assume that it's Gaussian noise, or we expect it to be Gaussian noise, but we're going to say with a standard deviation that's equal to sigma sub I. Okay. Questions about sort of where we're at this point? Because what I'm going to do now is I'm going to take my sigma sub d and my sigma sub I as representative of the noise and the data in the image domain, and talk about how that actually relates to things that we care about, things that we might control in an imaging experiment. So I'm going to flip over. Alrighty, so if you go back to that expression, it comes out of what was labeled as 8.42, both in the notes I just went through and what's in the book. Then you can draw out the relationship that the image domain noise squared is equal to 1 over n times the data domain noise squared. And so this is actually a really interesting and important relationship for MR. It comes out of the work by Richard Ernst, actually, who was one of the first to recognize the importance of doing imaging in the Fourier domain. And what this expression tells us, and the reason it's so relevant and perhaps important, is that it basically says that Fourier encoding, the strategy that we like to use, is equivalent to endpoint averaging. And I'll describe what I mean by that in just a second. And this comes out of, I think it's 844. And so if we look at this expression here, n is just the number of data points collected, basically, right? So the number of points. If you think about, say, the readout gradient, the readout gradient is sampling 128 points in k-space. Well, if you do, in fact, collect 128 points in k-space, then you've pushed down the variance in the image domain by 1 over 128. And that's akin to something like averaging. And so that's a really valuable thing, right? So that the more points of data that we're collecting, the better and better job we do of suppressing noise. Now, the more data points we collect, it also requires more time. Your readout gradient has to be longer. You have to acquire data for a longer period of time generally. And we'll talk about what the consequences of that are in just a second. But the idea that we get this effect of sort of endpoint averaging is valuable. We can just take the square root of each side, and this will be useful in just a second. So we just get 1 over square root of n times sigma d. And we would recognize, I just sort of said it too, but if we want to collect, say, n points, that takes time t. right? And so if you increase n, you're therefore going to increase time. And as a consequence, you have that the number of points you acquire is proportional to the time that you acquire data for. So we're going to make a substitution in just a second that says, well, let's not really worry about the number of points that we actually acquire. Let's just talk about time. How long did we actually acquire the data for? And so you can think about how long is your readout gradient, how many points did you measure during your readout gradient. You could also think of time as being how many times did you acquire the same K point. Maybe you did averaging in your experiment. You repeated the experiment 16 times, averaged all of that data. That, of course, would take more time, and you would have had more samples of n as well, whatever n is in that particular case. And so by making this sort of proportionality substitution here for the number of points and the amount of time it takes to sample things, we can say that the standard deviation in the image domain is just 1 over square root of time times sigma d. So this gives us some insight to the underlying variance in the image domain, the standard deviation of the noise in the image domain. In principle, we want to acquire it for as long as we can, but unfortunately, we have this square root penalty that works a little bit against us. So if I, for example, want my variance to go down by a factor of 2, how much longer do I have to scan for? I want this to go down by 2. 4 times, right? So I have this kind of penalty that works against me. Scan time is expensive, right? We'll go through some other examples of this, but if I scan for 4 times as long, then I have 1 over root 4, it's half. So my image noise is going to be half of my data domain noise. So that's good. I pushed my noise down, but I also had to scan for 4 times as long. So you could think of that as repeating the acquisition 4 times and averaging your data over the 4 acquisitions or something like that. There's different ways to sort of spend that time. So this is all just about the noise. Let's think about our signal, the signal itself, because what we're interested in is an expression that relates this to the signal to noise and parameters that we actually control. So just recall that the signal, say, in the image domain, and you can think of this as just like the pixel level signal. We're just thinking about pixels rather than, say, whole images right now. The amount of signal that you get is going to be proportional to 1 over n delta k. And why did I write it that way? Well, that expression there is the same as my field of view divided by n. Okay. And that's just an expression for, say, in a particular direction. This could be an expression for, say, delta x, or my spatial resolution. So if I increase my field of view, but I keep the number of encoding points the same, then the pixel width has gotten larger, right? FOV goes up, and my pixel width goes larger. That should necessarily lead to an increase in my available signal, right? So the smaller my dimension is, the less and less signal I'm going to have. So we know that the dimensionality of the thing we're imaging, or the pixels that we're using to image, has a linear relationship to the underlying available signal, if you will. So the signal to noise then just comes from the ratio of the available signal and the underlying noise. And so it's just the measure of the S sub I divided by sigma sum I. And we know that that's proportional through the signal expression we had just above to 1 over n delta k for the signal component of this. And then for the image signal variance, if you will, the noise component, that's just equal to square root of time over noise in the data domain. So just by substitution of those first 2 expressions, we can come up with an SNR expression that looks something like this. That expression itself, we already said it a second ago, but this leading expression here is just the field of view divided by n. And those are things that we control, right? On the scanner tonight, you can control the field of view, you can control the number of encoding points, and that controls the available signal coming from an individual pixel, if you will. And then this expression on the right-hand side, if we're just talking in terms of proportionalities, we could take the variance of the data noise itself to be an uncontrolled but constant parameter, and so then we only really care about the amount of time we have for imaging. And I should point out that this is really just the example in one dimension. And so this here gives you effectively the pixel size in one dimension, and this tells you that your signal to noise depends on both the pixel size and the square root of time used to acquire data, or time spent acquiring data. We could expand this to sort of a more three-dimensional sense and say that what it really depends on is the voxel volume and the square root of time, or scan time. And so this is the most basic sort of SNR relationship that we have in MR. And so this first term here we take as what we call the voxel volume. And the nice thing about this expression here, and I'll show you in just a second, but this is largely governed by parameters that we control. So do you know what I mean when I say voxel volume? We don't think in terms of pixels, we think in terms of 3D, so voxel volume. So there's different elements that comprise your voxel volume, right? It has to do with your field of view in the x direction and your field of view in the y direction. It has to do with the number of points in the x direction, the number of points in the y direction. And then it depends also on your slice thickness, right? Really thick slices are going to have much larger voxel volumes and consequently have higher signal to noise. This expression also tells us that scan time, while it's important to our overall signal to noise, if we decrease it, say by a factor of 4, then we have a pretty severe penalty on our SNR. And if we increase it by a factor of 4, it helps our signal to noise, but only by a factor of 2. So this square root property here is sort of works against us for the most part. You'd like not to have it depend on the square root idea. So what I'm going to do is flip back over to the slides, and we're going to think more carefully about what this relationship means. Again, it'll be related to things that you work on in the lab tonight, but I want to tie it into sort of the parameters that you might actually control on the scanner or in the design of any imaging experiment. Questions about sort of how I got through this? Yeah, come on.
How did we lose the signal?
It's just a proportionality here. So here I'm just saying, well, I could leave the sigma d in there, but I don't control it. So I didn't, because it's effectively a constant, you have a level of noise for the imaging system. So let's just assume that it's a constant. Leave it out because we're only talking about proportionalities anyway, and then we can just have an expression that depends on things we actually control. You could leave the sigma d in there. We just can't adjust it per se. It's a component that the sigma d itself. So what does sigma d depend on? Sigma d is noise in your system. And so it depends on like the electronics of your system, right? It depends on like your coil. You might have a noisy coil or a really high performance coil. You might have a noisy data acquisition board or a really high performance data acquisition board. Something else that it depends on is so-called body noise. And that means that each of our bodies themselves, because of very small currents and magnetic fields that exist in us when RF fields are played and gradient fields are played, you will have your noise creating, or your body rather, creating noise in the image itself as well. So bottom line, sigma d isn't something we control, so I just sort of left it out so we could focus on the things that we do adjust. Okay?
Well, why the signal intensity is proportional to spatial resolution?
I didn't sort of draw out a real analytic expression here. You're looking at this here. This isn't here we're saying that the signal is dependent on, say, the field of view divided by the number of points. And all I want you to have in mind is that this here is a measure of spatial resolution, right? Like delta x, right? If delta x is really big, then I must have a lot more protons. And if I have twice as many protons, then I have twice as much signal. So depending on if my delta x gets twice as big, then my signal should go up by a factor of 2. If my delta x goes down by a factor of 2, then my signal should go down by a factor of 2. This is just, again, sort of in a single dimension. We were just using the description in that one dimension. We'll talk more carefully in just a second about what happens when we change the actual voxel volume.
So you only talk about like single pixel.
Yes. This is an expression for the signal to noise, say, at a pixel location. And in general, that's what we actually care about. You might, if you're doing some experiment, you might say, oh, well, I just want to know the signal to noise in this homogeneous region. But in principle, we really want to characterize things at the pixel level. We may generalize it to have some summary result, but we care about things at the pixel. Okay? Okay. So we're basically just going to expand that expression a little bit and look at some different things that it means. So on the top here is the same expression that we just ended with, and where V is the voxel volume. So it depends on the product of the slice thickness, your X resolution, and your Y resolution. And the resolution itself I take to mean the field of view along the X direction divided by the number of points encoded along the KX direction. In an MR, we can control the field of view in either direction, right? We can, and you can do this in your experiments tonight if you want to. You can adjust the field of view to have, a greater or lesser extent left-right and a greater or lesser extent up-down. Those are independently controlled parameters. What you should be thinking about in your head is you're changing delta K, either in the X direction to adjust the X field of view, or delta K in the Y direction to adjust the Y field of view. And those are just independent parameters. I could adjust delta K freely with no effect on delta KY, and I could change delta KY without affecting delta KX. This time parameter that we were talking about really refers to time spent acquiring data, right? We'll talk about some other sort of time-related parameters in just a second. But what that really means is, what's the number of KX points you acquired? That's proportional to the time you spend acquiring data is proportional to the number of KX points you acquire, the number of KY points you acquire, maybe the number of averages, right? We can repeat that experiment 2 times or 32 times, and that'll be repetitions of K points, and it will extend your acquisition time. What's a little bit less obvious here is that bandwidth enters in. This is the acquisition bandwidth, or the bandwidth of the readout gradient. And the reason that enters in is the bandwidth itself adjusts how quickly you move through K-space, right? So you need a strong gradient to have a high bandwidth readout gradient. And that means that you'll be getting those K points very quickly in time. So you might have 128 points, but if you acquire those with low bandwidth, it'll go slowly across K-space. And if you increase your bandwidth, then you're going to go across K-space very quickly. And so bandwidth affects it's inversely proportional to the amount of time you spend acquiring data. We'll talk a little bit about bandwidth because it affects some image quality features as well. But it's related, your bandwidth is directly related to your signal to noise. So tonight, when you're thinking about your experiments, that's a parameter that you'll want to pay some attention to. And so we can basically expand this first and relatively simple expression into a handful of parameters that we actually control. And so when it comes to voxel volume, those are all on the front end here. Field of view along the X direction and the number of points along the X direction, times the field of view in the Y direction and the number of points in the Y direction. And H we take as the slice thickness. So these 3 things, the product of these 3 things gives you the voxel volume. And this is all just through proportionality. This is just helping us understand if the signal to noise goes up or if the signal to noise goes down by parameters that we routinely control on the scanner. And we would expect, let's just take the simple case of averaging. If I increase the number of averages by a factor of 2 or 32, then I expect to increase my signal to noise, but I'll do slow at a sort of decreasing rate because it comes in as a square root factor. So I need a lot of averages, say 16 averages, to get a 4-fold increase in my signal to noise. So getting doublings and triplings and quadruplings of signal to noise is usually pretty expensive, so to speak, in MR terms. And then in a similar way, it depends on how many total NKX points or NKY points you're also acquiring. And it's inversely proportional to the bandwidth, because the bandwidth is how quickly you're moving across K-space. So you want this parameter to be relatively low or very low when it comes to signal to noise. There's some trade-offs. We'll talk about bandwidth a little bit later. But when bandwidth is low, you'll have high signal to noise, but you'll have high chemical shift. And we'll see that when we talk some more about artifacts. kx. So this is a good expression. I think this or something almost identical to it shows up in the write-up for the lab tonight as well, because you'll want to keep this in mind. And the scanner itself, you should ask the TAs. I'll try to remind you guys when you're there. But the scanner itself, when you pull up a protocol, kind of in the middle right-hand side of the screen, you'll see a dialogue or a little text string that says R SNR. And R is the relative SNR. You pull up a protocol, and the scanner says the R SNR is 1. Just some relative SNR. If you ran this protocol, I'm going to define that as having whatever happened, whatever you acquire, that has an SNR of 1 in some relative unit space. And behind the scenes, it will use this expression so that if you change averages, you'll see what happens to your relative signal to noise. So you can do that tonight. You can change your averages. You'll open up a protocol. The relative signal to noise will be 1. You go into averages. You increase the averages by 4. And what happens to your relative SNR? Doubles, goes to 2, right? So you'll see these trade-offs. And the reason that's handy is this relationship isn't complicated, but it's a little bit screwy because you'll see the number of encoding points shows up in the numerator inside the square root, but in the denominator for voxel size. So there's this kind of total trade-off. You could write it out. This, I think, is a little bit more intuitive to think about. If you want to, you can collapse these nkx terms down to something that's a square root of 5. But bottom line, that's an easy way on the scanner to know, oh, if I change those 7 things to my protocol, is my SNR going to be better, worse, or the same? Gives you some ballpark insight. What this expression doesn't take into account at all is anything about like T1 or T2 or gradient echo or spin echo, right? This is just really sort of like bulk acquisition parameters that are independent of the underlying sort of signal levels themselves. The signal levels are really dependent on whether you played an inversion pulse and are you using a refocusing pulse and what was your flip angle. And those things don't enter at all into this equation, which is just a proportionality relationship to actual signals. Okay, so we've gone through a few examples like this. I might do this a little bit quickly, but we know that if we have the slice thickness, so if we take the slice thickness here down by a factor of 2, I need to have 4 times averaging if I want to maintain my signal to noise. So if this goes down by 2, this has to go up by 4, so that the net product is no change. A different example would be this. I could double my slice thickness. I could say, what I'm really after is signal to noise. I'm not too worried about my voxel volume. I'm going to go ahead and double my slice thickness. What does that do to my signal to noise? Well, you actually only need to acquire 25% as much data. If you could find a way to reduce your acquisition to do so, then you would actually maintain your signal to noise. Alternately, if you double your slice thickness, then you'll just directly double your signal to noise. Another example, in general, the field of view is fixed, right? You pick a field of view that encompasses the object that you care about, so it's fixed. If you want to increase the resolution, then you're going to increase, say, nkx and or nky. Because nkx and nky enter in sort of 2 different aspects of this expression as it's written, this will ultimately increase your scan time, and the SNR will actually decrease. So you didn't come out ahead in doing that, right? So you might look at this expression and say, okay, well, if I increase nkx, that's obviously going to decrease my voxel volume, so my signal to noise should go down. But I'm increasing nkx, and it's in the numerator, but it's inside a square root, so it should improve my signal to noise, but it doesn't do so enough to offset the SNR loss due to the resolution changes. This is a little bit more easily seen if you collapse these nkx terms where they show up just in the numerator, just in the denominator as a square root of nkx term. And these kinds of examples would be very simple things to expect the final exam, for example, too. So there are lots of parameters that affect our signal to noise, but that relationship only captures some of them, and this is what I was talking about just a second ago. It doesn't really characterize anything about whether you use a gradient echo or a spin echo. It doesn't say anything about TR, TE, TI, flip angle. It does say things about your field of view, your slice thickness, your matrix size, and your bandwidth. So it's important to understand what that relationship is useful for understanding. And it is a pretty handy thing. Like I said, you have this RSNR value that shows up on the screen. So if you're working with an otherwise kind of fixed parameter and you're just trying to adjust it to give you the level of detail and the field of view that matches your object, then that can be a useful sort of feedback for knowing whether you're likely to get a better image or maybe a poorer image before you run a 5-minute scan or a 6-minute scan. So keep that in mind tonight. The other thing you have to keep in mind is that if you take a protocol and you just copy and paste it, the first time you open a protocol, it'll have a relative signal to noise of 1. If you change some parameter and run that, that then becomes the relative signal to noise of 1. So it's always sort of normalizing against itself. So while you're in a protocol, you'll see this now, but while you're in a protocol making adjustments, the relative SNR can go up and down. But then if you copy that protocol and run it again, it resets back to just being an RSNR of 1. So it's always relative to the starting point, if you will. If you see it in action, it'll probably make just a little bit more sense. Okay, so anyway, lots of other factors here govern our signal to noise, and you guys have seen sort of how this all plays in, but obviously the TR itself and the TE itself governs contrast and signal availability. And we pick those things to have the image contrast that we want, but they do at some level have an impact on our signal to noise as well. The noise in our system is relatively constant. It's affected by things that are pretty fixed about the imaging system. It's the signal level that we have a lot of control over. Right? We can control signal amplitudes through inversion pulses and refocusing pulses and gradient echoes and everything else. And of course, we can control the overall signal level by switching field strengths. We can go to a 3T scanner or a 7T scanner. That gives us more net polarization, more bulk magnetization to work with. But those aren't sort of considered or described in that relatively simple signal to noise expression. Okay, so hopefully we have some idea for what noise is. What I want to do is spend just a few slides talking about what we call multi-coil reconstruction. And so you'll remember when we talked about coils, we said that coils have magnitudes and phase. So when we measure signals, we have both of these underlying components. And the coils themselves, while they may be constructed very, very similarly, meaning the electronics of two coils are identical, say, we position them in different parts of the body, and consequently they see different parts of the body. So here I'm showing that I have coil 1, and coil 1 is obviously at the bottom of this phantom because it's getting nice bright signals from tissues or regions that are close to the coil itself. And this image reconstructed from coil 2 over here, the coil must be in a position that's approximately here because they're getting nice bright signals from that region of interest. So even though these two coils are identically constructed, where they are relative to the object, of course, colors information that's in that image. They don't just have magnitude, they also have phase. We talked about phase when we were talking about the whole signal acquisition chain. We won't really talk about phase further today. And so what we remember is that when we're imaging someone or objects that you'll be imaging in the lab tonight, we'll place coils anteriorly on the chest. We may place coils posteriorly as well. Those coils might be embedded in the table. They typically are, or you have a head coil that you sort of slide your head into. But there are a number of different coil elements. It's sometimes confusing. We might call it a head coil. We might call it usually call it a multi-channel head coil, meaning that each of these individual receivers is sometimes called a coil, sometimes called a channel. It's probably more accurate to call them channels. But bottom line, they'll see different parts of the anatomy according to how they're sort of geometrically placed on the anatomy. And you can, everything that we've basically been talking about has been acquiring case-based data for a single channel receiver. And the very simple question I want to answer now is, well, how do you combine all of this data so that you can reconstruct an image that is uniform over the field of view? These images won't be uniform over the individual images won't be uniform over the field of view. And so if we just reconstruct images from individual channels, you'll get images that look something like this. And none of the individual images is especially satisfactory. They have bright spots and they have dark spots, but were we able to sort of combine that information together, we'd have a much more homogeneous, sort of flat appearance of the underlying images. So it's relatively simple what we need to do. Our job is just to take the imaging information from the jth coil. So let's say we have a total of j coils. It might be 4 coils. It might be 42 coils. We're just going to take the magnitude data from each of those individual coils, but we're going to normalize it by what's called the coil noise, or the noise variance. There are actually ways built into the system to estimate coil noise, so they can just turn on the ADC and measure background noise without doing any sort of imaging experiment. And the reason that's really important is some of your channels, some of your individual coils may be really, really noisy, and some of them may be high SNR performance. And you don't want to just add those things together, because you might be adding in a bunch of low signal to noise data on top of really high signal to noise data, and therefore sort of just treating them uniformly. What you'd rather do is normalize by the underlying noise variance. So if you have a really low noise variance, then it overweights or heavily weights the imaging information. And if you have a really big noise variance, a big noise variance is bad, right? That means you have a really noisy image. So if your noise variance is really, really big, you want to suppress the image contribution coming from that particular channel. So this is just a square root sum of the squares of the image information, the image scalar information, normalized by the signal to noise. So this happens after the Fourier reconstruction process. And so we can add them all up. And the advantage then is that we can combine, say, multiple channels into an image that's much more homogeneous over the whole field of view. And so this image, composited in that same way from those 4 different coils, gives us a much better image. The other thing that's nice about, and this wasn't sort of obvious at first, the first coils that were built were more like birdcage coils, meaning they were coils that encompass the whole body and you slid into the coil. The downside to that kind of coil design was those really big coils were also capturing noise from very large volumes, right? If you have a really big coil, then you're sensitive to any signals from within the sensitive volume of that coil. So a really big coil is sensitive to a really big volume. And that meant you were also capturing a lot of noise. When you deal with individual channels like this individual coil element over here, it can't pick up noise from really distant regions. And so that noise doesn't add into or contribute to corrupting the underlying image. Whereas if you had a so-called birdcage coil that covered the entire body with a single coil, you actually have poor noise performance. So throughout probably like mid-90s through the early 2000s, there was a period of development going from single channel systems to multi-channel systems. And it started off something like this. Well, if 2 channels is better than 1, then 4 must be better than 2. And then wasn't 16 better? And then, well, what about 32? And it kind of rolled off at about 32, meaning that when you get past that, for most applications, there's very limited benefit. But a lot of high-performance imaging centers will be routinely using somewhere between 16 and 32 channels for most of their acquisition protocols. I saw that already. Let me remind myself of where we are. Yeah, typical, right? Slide 25, and I have maybe 100 slides prepared. It's good. It's good. Let's go ahead and take a couple-minute break because it's 2:05, and then we'll come back and we'll get through as much of artifacts as we can. I'll see if I can figure out a good way to. I knew we wouldn't get to one section, but I think we can get through most of what I wanted to get to. Yeah, I'll take a couple-minute break, guys. Yeah. Yeah.
This is multi-coil, right?
Yes. There's different ways to do it, but you don't actually have to do like an imaging experiment, right? So think of it, someone's lying in a scanner, and there's time when where the patient is waiting because the technician is getting ready to do the next thing, right? So if at that point in time, you just turn on your receiver system without any excitation, without any imaging pulse, without anything, you can just measure the noise in your system. So you don't have to do anything. And so that can happen kind of in the background. And they can do that. They can receive data from all of the coils and then look at the variance of that recorded signal.
that means that I just put like the coil there and I just read the signal that they trying to
Yeah, yeah. There's no excitation. There's nothing. It's just the noise, and then you have a way of knowing whether that's a really noisy coil or that's the really noisy coil. Because you look at the variance, and you say, okay, look at this coil. It's going crazy. Who knows why? And then look at this coil. And it's hardly doing anything. So then you just get that simple signal to use.
And this signal is the one that I'm receiving. It's not.
No, that's just to give you the variance here.
Okay.
Right. This is the image reconstructed from each coil.
Okay, I get it.
Yeah, and then you add all that up. You're just normalizing. So you get rid of the bad coils.
I get it.
There's some bad coil, you just get rid of it. And then you add it all.
Yeah, because the variance is very big.
Exactly, yeah. So then that signal, that contribution just goes down. Yeah.
Okay.
So there we go.
I get it.
That's a good question.
I had done this one. I had no idea if I knew it. Yeah. and then the like prelim.
I want to conference and have presentation.
Yeah.
And I want to go there on Monday.
Yeah.
So I might want to like see earlier in the day so I can share the day when in San Diego.
Okay, yeah, so sorry, what are you asking for which? I didn't hear the first part. The next
Monday.
lecture?
Yeah, if I miss it, but I will watch the video.
Yeah, so I mean, I don't feel too strongly about it because it's available online. The material is just as important as any other lecture. You won't have a homework on it, but it'll be on the final. But no, I understand. I mean, there's always stuff.
Yeah.
Welcome to grad school.
Yes.
So just down to San Diego.
Yes.
What's the
What
name?
are you including the seminar?
Oh, yeah, that's a really good meeting. Yeah.
You don't have to listen.
I don't know. I never have actually, but I have a couple. I have really good colleagues that go through the routine and stuff. So I should look at it because it's so easy. It's so close.
Yes.
Yeah, good. But yeah, fortunately things are online. So. All right, guys, I'm going to go ahead and get underway. We'll see sort of how far this material we get through. I want to get through as much as we can. Hopefully I don't sort of like rattle on and on too much. But it is related to the lab tonight, so in that way it's important. There's a big chunk at the end that's sort of like protocol optimization that I'd like you guys to look at, but we probably won't get to it. But it kind of stands on its own pretty well, I think. So anyway, artifacts. So we've actually talked about artifacts kind of here and there throughout the course and sort of different of the lectures. And these are all different artifacts that you should understand. We haven't talked about each of these yet, but we've talked about many of them, and we're going to talk about the other ones as we go through this. So keep these in mind. I always ask an artifact question on the final. So give you guys too many hints, but it's there. Okay, so let's talk about chemical shift for a little bit. We know that gradients provide a linear variation in frequency, right? We turn on a gradient, we can get something over here to be high frequency, something over here to be low frequency, and it's a linear variation between those 2 points. Fat, interestingly, because those hydrogen molecule or hydrogen atoms are in a different chemical environment, they're usually bound as CH2 and CH3 groups forming triglycerides. They actually have a lower, effectively have a lower Larmor frequency. It's the same gyromagnetic ratio, it's still proton, but because of the local chemical environment, they're actually shielded some, they interact with each other, and that causes them to precess at a slightly different frequency than water protons. And in fact, that frequency difference is about minus 220 hertz lower than water, 1.5 Tesla, and it's field strength dependent, so it's even lower, it's even larger shift at 3 Tesla. And I'll show you the sort of imaging consequences of this in just a second. But it's helpful to remember that the scanner really is a frequency detector, right? What we measure and sample all the time is frequency data. That's all of K-space after all, right? And then we use that frequency information to help us build a spatial position map or an image based on those spatial frequencies. The scanner, though, it has to assume some things, and it basically assumes first that everything is water, right? And secondly, or as a consequence of that, fat, which is going to be at a lower frequency, is interpreted as just being lower frequency water, right? It can't distinguish the chemical environments of these different things. You could with sort of the right imaging or spectroscopy experiment, but a priori, we have to assume everything behaves like water. And because fat precesses at a different frequency than water, it gets misregistered. It gets misinterpreted. Its spatial position gets misinterpreted. The figure on the bottom is just demonstrating that this is maybe the applied gradient, meaning that the gradient has no frequency effect at isocenter, and it has a stronger and stronger frequency offset as you get more distant from isocenter. And if we had a pixel that we cared about that had a width delta x, that would correspond, according to the applied gradient, to having a frequency distribution across that pixel of delta f. So we can change the strength of our gradients, and we can change the frequency content of an individual pixel. Unfortunately, fat, because it behaves or precesses at a slightly different frequency, it's as if you've offset the effects of this gradient, meaning that the effective field for things that are fat in the presence of a gradient is such that things at this spatial position will occupy the same frequency as water at this spatial position. So because the water at this spatial position and the fat at this spatial position precess at the same frequency, you have a problem. You can't distinguish those things as actually being from different spatial positions, because all you have access to is frequency information. And so this leads to a chemical shift artifact. Here's an example of what that looks like. So here on the left-hand side, you have a low bandwidth image. We'll talk about that a little bit as well, but low bandwidth images are going to give you large water fat shifts or fat water shifts. Low bandwidth imaging will also give you higher signal to noise. So we saw this trade-off in the signal to noise expression of the bandwidth was in the denominator of the square root component. So low bandwidth is nice in that it gives you high signal to noise, but it also gives you high chemical shift. So if you compare these two images from the left and from the right-hand side image here, this is a high bandwidth image, but that means it's going to be lower signal to noise. So you can see the noise, especially kind of in the bottom part of this image in particular. But it also has a lower chemical shift. And so you don't see, for example, this fat signal here at the top is shifted sort of outside of the skull. And it's shifted, you'll see a dark band in between here because that those fatty tissues have shifted up and away from sort of their true anatomical position. Whereas in the right-hand image here, you have sort of good registration of watery skin and the subcutaneous fat. Everything is sort of spatially registered where it should be registered. High bandwidth pulse sequences, they're good and bad. They're going to degrade your overall signal to noise, but they'll reduce that chemical shift artifact. There are different ways of dealing with fat, and we'll talk about some of that today. And in particular, we can use so-called fat saturation pulses or fat water separation techniques to treat and deal with fat and water in very different ways. And I'll talk relatively quickly about ways of dealing with fat. So we'll come back to that sort of chemical shift concept in a little bit again. You can sometimes think of artifacts as phase encoding artifacts or frequency encoding artifacts. So we've talked already about a very common phase encoding artifact. You guys remember what that would be? Aliasing. So aliasing is basically associated with being a phase encoding artifact. That's a good thing to remember. There's a reason, we haven't talked about it, but there's a reason that we won't see aliasing in the readout direction. For those with a strong signal processing background, we basically oversample in the readout direction, so we avoid the possibility of encountering aliasing in the readout direction. So aliasing is very much a phase encoding artifact, but I also want to talk about some frequency encoding artifacts. So this we saw just a second ago, that there is a range of spatial positions. This might be the left side of a pixel and the right side of a pixel, and that pixel has some width delta x. In the presence of an applied gradient, a pixel with a width delta x is going to also have precessional frequencies over a range delta f. And if I change my gradient strength, I can make my gradient strength larger, then I can make my pixel size actually smaller. Or I can make my gradient weaker, and I can make my pixel size to be even wider. So you can think of changing your pixel width by changing the slope of this blue line that represents the applied field from the gradient, and you can make that slope higher with a strong gradient, or you can make it lower with a weak gradient. And this basic concept of turning on a gradient when we acquire our data leads to various frequency encoding artifacts. So the thing to have in mind is this brief period of time where we turn on a readout gradient, similar to this blue line that's shown, and you turn that gradient on for a period of time while you're acquiring your data. So while you're acquiring your data, fat, for example, is doing one thing at a frequency that's the Larmor frequency of fat, and water is doing a different thing. This leads to the chemical shift artifact that we saw just a second ago. So here's another way of sort of thinking about it, and this will be in a slightly different context. This will be in the context of severe off-resonance. And we can have severe off-resonance, for example, when we have an implanted metallic implant. Right? So this happens all the time. Someone has a spinal implant, a knee implant, a hip implant, orthodontic hardware, whatever. And that's a source of severe off-resonance. They significantly perturb the local magnetic field. So on the top is just normal spins, and normal spins in the presence of a gradient will have a range of spatial frequencies, a range of Larmor frequencies, right? And so we can see that these are precessing at different frequencies. In the case of off-resonance, or perhaps severe off-resonance, you can see that these two spins here actually are precessing at the same Larmor frequency. So the gradient wants this spin to precess at this frequency, but some source of off-resonance is causing it to precess at a lower frequency. And so these two spins appear from the acquisition side to be precessing with the same frequency. And so that causes this problem. It means that those populations of spins appear to us to be coming from the same spatial location, right? They have the same frequency. We associate frequency with spatial position, and we have this problem of not being able to separate out these two different signals. And so the problem is that you get so-called signal pileup. You get the signal rather coming from different populations of spins appearing at the same spatial location, but you'll also end up with spatial locations that have voids or signal losses. Now, the actual effect in the presence of, in this case, a knee implant is really complicated, right? The field effects are really complicated. You get all kinds of very heterogeneous magnetic fields in this region of interest. But you can see it qualitatively that you have these regions of significant signal pileup, meaning all of the signal from a bunch of different spatial locations has landed in such a way that it appears to be coming from this little arc of signal here. And then you also have regions where you'll get, say, signal voids. Maybe this is an example of a signal void here. You'll, of course, get signal voids like where the device itself is located, right? You don't expect to generate an NMR signal from a titanium knee implant itself. So there's going to be a void from that as well. But the field effect will give rise to this apparent pileup and signal loss as well. Thinking also along the lines of frequency encoding artifacts, our gradients we know... yeah, please.
I don't understand how that last part is different from the chemical shift.
It's the same, just different magnitudes of the effect. And so it's a great question. So when we talked about the frequency shift that would happen with fat or chemical shift, it was like a couple hundred hertz or a few hundred hertz. This might be 2 kilohertz or 10 kilohertz because you've got a big metallic object that's there. But the physical principle is the same. So I'm glad you could tell the difference. Okay, so we talked about, this came up in one of your homework assignments, so I'll go through this relatively quickly so I can get through some other material. But we have this basic assumption in MR that the Z component of the B field, right, gradients only adjust the Z component of the B field, created by those gradient coils varies linearly with X, Y, or Z over the field of view. And there's a lot of engineering that goes into making sure that these systems perform as linearly as possible, but of course they're not absolutely perfect. And as we push towards higher gradient amplitudes and higher slew rates, which overall improve system performance, they sometimes can only be achieved by compromising on spatial linearity. So we want high strength gradients that are really, really fast, or imaging times can be pushed down, but it's hard to maintain all performance aspects in doing so. And so the consequence is that subtle underlying gradient nonlinearity causes geometric distortion, and it can cause intensity distortions. So this figure we've sort of seen before. You saw it in your homework. You ideally have a linear gradient, but because of some imperfections in the system, it behaves linear, slightly non-linearly or maybe very non-linearly. So again, this mapping between space and frequency gets thrown off from what we expect or what we intended for the system to be doing. And this is the sort of practical or real consequence of what you would see. So the left-hand side here, this is a large field of view image. So you're especially going to see these kinds of nonlinearity artifacts when you have large fields of view. If you're just looking at the middle 5 centimeters of the scanner, you won't notice this. But here, we've got maybe an image that's 50 centimeters or maybe even 60 centimeters field of view. And on the left-hand side, you can see that things perhaps look a little unusual. And if it's not obvious on the left-hand side that it's unusual, just simply compare it to what's happening on the right-hand side. And so you can see that there's this pinching towards the legs, right? The anatomy is being sort of pinched together at the bottom. And as a consequence of being pinched together at the bottom, you're also getting signal pileup, right? Those protons are being forced to appear as if they're coming from the same pixel. And so you can see that the signal that's coming from this, say, most pinched together region down here is also brighter as well as geometrically distorted. So this is what the system is sort of natively able to acquire. And this is the image that you would sort of get if you just took your K data from the gradients as they perform. Meaning to recover the image that's shown on the right-hand side here is actually an image processing step, or it has to happen somewhere in the reconstruction chain where you know the nonlinear performance of your gradient system and you use that to inform the reconstruction of your image. Oftentimes this is done through just what's called gradient warping. They're simply warping this image with a known distortion field. They've measured, evaluated the distortion of their gradient set, and they just apply that distortion in the inverse sense to all of their images to unwarp the underlying images. Okay. Moving a little quickly here if I can. Okay, so another possible artifact, this is an example of when it's really important to go back to K-space. So again, if you ever work in research, it can be really useful to look at the K data when you get an artifact, because while there is a linear transformation through the Fourier transform between your K-space data and your imaging data, we don't do that well in our heads, typically. So this idea of data clipping, it'll give you a very obvious image artifact, but you may not really recognize what's causing it unless you went back to your K data. And the idea is that your received signal actually saturates your receiver. So you have some receiver system that's expecting, say, a certain voltage in that underlying signal that it's going to receive. And it adjusts various gains so that the voltages it's going to record fall within the range it's able to measure, plus minus 5 volts, whatever it is. But if the amount of signal that comes through the system actually exceeds the calibrated range, then you'll saturate. And that means that a bunch of your K points that are high in value will hit some maximum and just be clipped. They can't exceed the maximum value that the system is able to measure, and they all just get pegged at the top. So usually the peak signal is in the middle of K-space, and so you're going to lose some low spatial frequency information. Something about your middle of K-space is going to effectively just be sort of cut off, if you will. And if it's affecting the middle of K-space, then it's going to have something to do with your overall sort of contrast, your overall intensity of the underlying images. Usually through pre-scanning, we can avoid this. We can get a test voltage, we can adjust our gains to make sure we don't overrange our receiver system. But if for some reason something unexpected happens or the calibration is off, you could saturate your receiver. So the left-hand side is sort of what you would expect. You've got a 2D Fourier data, and you do the 2D K-space data, do the Fourier transform, and just recover a relatively good-looking image. On the right-hand side here, this is all the data sort of multiplied by a factor of 10 or 100 and then clipped off so that you can't exceed a value of, say, 1024 or something like that. And then if you do the 2D Fourier transform, you'll get a really unusual image that looks like this. So here you can see something has happened where you end up with like kind of a haze or some sort of overall background contrast or signal intensity change. It's not obvious that this would happen through data clipping, right? But if you were to go back to your K-space data, you'd be able to sort of pick it up if you were to inspect it carefully. So there might be other reasons that you could get a similar artifact, and therefore going back to the K data might be the way to sort of unravel this, if you will. It's not an artifact we see very often anymore. It's sort of like historically could happen, but now the systems are pretty good at self-calibrating to avoid things like that. We've seen noisy spike artifacts before. You saw it in lecture, you saw it in the homework, and the simple idea is that if we have a point in k-space and its amplitude is significantly overrepresented or it's significantly higher than it should be, then you'll get some banding artifact across the underlying image. Again, this used to be something that sort of old analog systems would sort of show up from time to time, or if you have faulty hardware. Sometimes when a coil is going out, you've got a coil that you've been using for 10 years and it's pretty well used and showing its age, you can start getting sort of little voltage spikes in the receive system that'll lead to a spike at the point at which you were acquiring some data. So we see things like this from time to time, but it's not too common. But again, it's another example of, in k-space, it's very clear what happened. It wouldn't be difficult to sort of significantly improve the image quality of the right-hand side just by going into your k data and manipulating this one particular k point. Okay, so lots of little artifacts, things to sort of keep in mind at least. One is what we call B1 inhomogeneity, right? So the B1 field that we talked about, we always assumed basically that when the B1 pulse was played, when the RF pulse was played, and we wanted a 90-degree pulse, that we got a 90-degree pulse across the whole field of view, right? It's a reasonable assumption, but in a practical imaging system, it won't necessarily be the case. And so here, this is just a uniform phantom, and they've placed some copper foil on one part of the phantom over here. And this means that the B1 field is not able to sort of penetrate or get into the object in this particular region over here, so it's effectively not excited. So this could look a little bit like a susceptibility artifact, meaning if I had a thicker plate of metal over here, I could perturb the field enough to actually cause a field offset that might lead to the signal amplitude being low. In this case, it's really thin copper foil that doesn't all by itself affect the susceptibility or the magnetic field, but the B1 field isn't able to sort of get into the object, if you will. And so B1 inhomogeneity, where you don't uniformly excite everything, is a problem. It's a problem because the systems themselves are not always perfect, and it can be a problem depending on sort of the exact geometry and configuration of the thing that you're trying to image. This is a pretty common one. We didn't have time to go through it in this class. You might see it in 229 if you take that class. This is a very common phase encode artifact. So again, we can usually categorize things as frequency encode artifacts or phase encode artifacts. Patients obviously will move during an imaging exam, and most of our imaging acquisitions will take anywhere from 5 seconds to maybe several minutes to acquire. And if there's patient motion during that acquisition interval, it'll lead to artifacts, but specifically lead to artifacts in the phase encode direction. So here you can see that this object was being, sort of moved or vibrated in the up-down direction, and you get this sort of ghosting artifact that's drifting off of, say, the anterior part or the posterior part of the coil. This is a pretty common artifact if someone is breathing while you're acquiring images in the abdomen or the chest. You'll see this sort of hazy, kind of rippling artifact. Because they're moving, and the spins are consequently moving while you have applied gradients on, you're going to end up with some stray signals that don't correspond well to representing the underlying object itself. So a very sort of typical phase encoder artifact, if you will. This looks a little bit similar to the B1 inhomogeneity artifact that we showed previously, but here we've got just a small, I think it's a nickel or a small metal dime placed adjacent to the coil. That's thicker and sufficiently large to cause a susceptibility artifact, meaning it significantly changes the local magnetic field and does so in such a way that you'll get some signal loss immediately adjacent to that coil, but you otherwise have good excitation of the underlying object. So you'll get susceptibility artifact anytime the B0 is perturbed, and it can happen physiologically in areas where you have different magnetic susceptibilities. So watery tissues have very much the same susceptibility or quite close, but air has a very different susceptibility. And so we'll get susceptibility artifacts where lung is adjacent to other tissues, for example, or at least you can see it in those circumstances. Metal being another obvious one. Metal has a very different susceptibility than tissues, and different than air, of course. This is one that actually shows up more often than I'd like. So this is radio frequency interference, right? We talked about much earlier, we were talking about B1 excitation. that the room itself had to be, or actually we were talking about the receiver system of the coils. The room itself has to be clad in copper to form a Faraday cage. And that Faraday cage keeps stray radio frequency energy from getting into the MR room and then potentially into the receiver system or the coil itself. These coils are extremely sensitive. They can easily pick up stray radio frequency energy. So if your scanner door is wide open, unfortunately it happens from time to time that people are running measurement equipment in and out of the scanner room. We actually have good ways of doing this, but people don't always use the good ways, and they'll leave a cable across these openings that are in the wall. It's called a penetration panel. So at any rate, those wires act like an antenna. They direct and carry radio frequency into the room, where the door is open and radio frequency energy gets into the room. Or if that room shielding itself is faulty, that could happen. Maybe you have a leak in the walls and don't know about it, and it's slowly pulling apart some seam between a bunch of copper sheets. Different things can happen. The consequence is that you usually get a really narrow sort of stripe artifact like this, meaning you've got a bunch of spatial frequency, you have a bunch of radio frequency energy that's affecting a very narrow range of spatial frequencies, and that shows up as a line or almost like a spike artifact in the image domain. So it can be useful, again, to think about what would be happening in the k-space domain to give me an image that looked something like this. Again, just an example of radio frequency interference. Okay, so I like these kinds of questions a lot. I threw it in here, but you're sure to see one on the final. It's at least somewhat similar to this, but now I have to make a new one. I can't use this one. So on the left-hand side, you have just the Shep-Logan phantom just created for MATLAB, and this is what the object is supposed to look like. And then on the right-hand side, you have a corrupted image. And the question is, how many artifacts can you see? I forget what's actually in the notes. The answer may be in the notes, but who wants to call out sort of some image artifacts? Just raise your hand.
Motion and vertical.
Motion in the vertical. So what do you see? So who was it? Sorry. Right. Yeah.
Banding, horizontal bands.
Maybe. So I think you're picking up on sort of the stuff that's up here.
And within the...
And sort of within here. So it does look a little bit like motion. What else does it look like? Gibbs ringing, right? So Gibbs ringing and motion artifacts, they can look kind of similar. Gibbs ringing has this real sort of like periodic pattern to it. Motion artifacts tend to be a little less sort of periodic. But that's still a good pickup. You're looking at the right sort of features for that. So Gibbs ringing we definitely see as well. Is Gibbs ringing a phase encode artifact or a frequency encode artifact? I heard phase. Who said phase? No one said. They were right. Who said phase? Why is it a phase encode artifact? That's the next question. What's that? Yeah. So if you look at this image here, how could you figure out what's the phase encode direction and what's the frequency encode direction? Any ideas? There's a couple different ways. It's a good one to figure out. What do you think? It's not. That would be a real trick. That's a great. Maybe I'll do that, but it's not. So phase encode is either up, down, or left, right. Does anyone want to guess if phase encode is up, down, or left, right? And not just guess, but maybe try to justify. Sure.
Is it up, down?
Why?
When you do the phase, at least in the k-space, you're transversing the ky direction.
Yeah.
You apply that to the image, and I think it stays the same.
It does. So, but what feature here are you seeing that helps you identify it?
Like the rings in the vertical.
Yeah. And so why would that? So you think up down is what, phase or frequency? Phase. Okay. So Gibbs, and then you're associating this is a phase encode direction because of the Gibbs ringing. Okay. Why? It's a good question. I mean, you're onto something. The question is like why.
Didn't you say horizontal and frequency direction? So
Yeah.
It's ringing that. Yeah, if it was frequency, then the horizontal.
So Gibbs ringing happens for high contrast, low resolution objects. So if we think of that, we have this array for Gibbs ringing. And as the image got to be higher and higher resolution, you just didn't see Gibbs ringing anymore. Okay? So it's a little bit of a tricky question. If you try to answer what I just asked, what's the phase encode direction, and you only do something about Gibbs ringing, Gibbs ringing and the phase encode direction probably go together because the phase encode direction is typically lower resolution for us. We pick our readout resolution. We're not too much limited in terms of acquisition time that way, but the number of phase encode steps really affects our total acquisition time, total imaging time. And so typically our phase encode direction is lower resolution. We might zero pad interpolate to square pixels, but typically phase encoding and Gibbs ringing are going to go together. Kamal said something really we picked up on from today's lecture, that we oversample in the readout direction as well. So typically you're not going to pick up Gibbs ringing in the readout direction. Yep.
So if for whatever reason we actually have lower resolution in X as opposed to Y, then it would be a frequency encoding reason for the Gibbs ringing.
You can have Gibbs ringing in phase or frequency encoding directions, but the lower the resolution, the more susceptible you are to Gibbs ringing. And typically an MR will have lower spatial resolution at the phase encode direction. There's some other ways, though. There's actually more than one way to pick up on what's phase or frequency. We were talking about chemical shifts a little while ago, right? So do you see a chemical shift artifact here? Yes, we said that. Yeah. So that actually tells us about the phase and frequency encoding direction as well. So if you look at this really bright signal on the outside here, this was simulated as being something like fat. Then you can see that that really bright signal is shifted to the right, right? So there's a big gap here where there's no signal because it's chemically shifted. Well, for you guys, it's chemically shifted to the right, and that causes pileup over here. So this whole fat ring is shifting over to the right, and that's a frequency encoding artifact. So chemical shift that causes a spatial frequency shift, that's a frequency encoding artifact. So we found Gibbs ringing, we found chemical shift. What else? Yeah. Maybe clipping, but I know how I programmed it, so there's no clipping. What else? Gradient nonlinearity, absolutely, right? So the geometry of this object here is not at all like the geometry of this object here, right? And you can pick it up in a couple different ways, but the overall geometry of the object is pinched. And then if you look really carefully in the corners, the object is just black. There was nothing to reconstruct in those locations because this object was sort of pinched in, okay? That's a little bit more of a subtlety. But bottom line, the geometry of this thing doesn't match the geometry of that thing. So that's 3 or 4 artifacts. There's at least 2 more. What's the first thing? One of the first things we talked about today in terms of artifacts? Noise, right? So this is obviously a noisy image, right? So that's no good. Different ways to deal with that, but it's obviously a noisy image. What else? We're talking about coils for a little while today.
Is there B1 collision?
It's a great question, or a great sort of suggestion, right? So if you look at the, was that you? Yeah. So why do you think that?
At the bottom right, it looks a little darker than this.
Yeah. So it's sort of dark over here and it's kind of bright over here, right? So this absolutely could be, and that would be a reasonable answer. This looks like B1 inhomogeneity. You have this sort of shading across the whole object. That could happen on different scales. So if you would provide that as an answer, I would go for it. It's not actually the case for how I created this problem, but it's a good answer, a very good answer. So there's something going on with shading. So if it's not B1 homogeneity, what is it? If it's B0 inhomogeneity, usually like a susceptibility artifact, that's usually going to be smaller. So the scale of that is usually smaller. What else?
Combined the coils.
Yeah. So what happened?
One coil probably had more noise.
Yeah.
So
Yeah.
the sigma term is larger. Get less.
Very good answer. So imagine you have a coil here, a coil here, a coil here, and a coil here. If this coil here has really poor performance, right? If the variance or standard deviation of its noise is really, really high, then that signal will be pushed down dramatically. Or maybe that coil was just missing. Maybe it wasn't even turned on. And so now you have this, what we call coil shading artifact across the whole object. I think that's all. I think that's it. That's good. Noise, gradient distortion, Gibbs ringing, chemical shift, coil shading. So you probably had that in your slides the whole time. Okay, so this is the last thing that we'll talk about, and then I'll wrap up. I'll point to some slides that you guys can look at. But I want to talk about gradient echoes and some special features and some special things that happen with fat in particular. So this we've seen a little bit already. So if we have water in a uniform magnetic field, everything just precesses at the same frequency. It's just the Larmor frequency everywhere, no surprise. We turn on a gradient, and if we look at waters and how they spin in a gradient field, then we know there's a distribution of frequencies across space in the presence of that gradient. And we saw this a second ago as well, that if one of these spins is a fat spin, and that fat is precessing also in the presence of a gradient, so the gradient is turned on, it affects the local field that causes the precessional frequency to be different. But because it's fat, the field causes the frequency to go up, and the fat causes the frequency to go down. You have this problem of fat and water precessing at the same frequency. And so this led to that chemical shift artifact that we had previously, where we get this signal overlap and we could get this signal void. So we have this problem in that what we measure is frequencies, and we make some assumptions about how frequencies map back to space, and that doesn't always work terrifically well. So here's just some examples again of chemical shift artifacts and acquiring images. Is the gradient echo image acquired with low bandwidth and high bandwidth. And so there's a couple things that we could look at these images and talk about. So the first thing is, what's the frequency encoding direction? Is it left, right, or up, down? And then, of course, why? Who wants to take a stab? UN.
Up, down.
Up, down is which?
Frequency.
Yeah, and how do you know?
Because in the figure on the left, there's the shift of the black line over the bone.
Yep.
So it's for the chemical shift.
Yep.
So it's frequency.
Perfect. And so you can see there's a signal void here. I'll point it out in just a second. And you can see that there's a signal pile up here, right? So this is brighter signal than you would expect. That might only be obvious when you have a comparison image, but we have the comparison image, so that helps. Another way that you might know is that when it comes to designing the imaging experiment, you usually want to put your longest dimension in the frequency encoding direction, right? Because frequency encoding is kind of free. It doesn't take you that long to get 128 points in the readout direction or 256 points in the readout direction. The difference is sort of at the hundreds of microseconds or milliseconds time scale. Phase encoding takes forever, right? Phase encoding takes a TR to get an extra phase encode step. It takes you microseconds to get an extra readout point. And so logically, when you build protocols, clinical imaging protocols, you're going to put the phase encode direction in the dimensional direction that has the lowest, would accord with the smallest field of view. So phase encoding for small dimensions makes sense, and frequency encoding for larger dimensions makes sense. Sometimes that doesn't matter. If you're doing axial imaging of the head, it's almost round, it's almost square, it doesn't really matter. If you're imaging the chest, it can make a huge difference, right? Because the aspect ratio of the chest can be 2 to 1, 2.5 to 1, or something like that. Of course, depending somewhat on the individual. So if we look here, we can see, especially when we have the two comparison images, we can see the signal pile up there, which is chemically shifted fat shifting towards the femur. And then you can see the signal void as fatty tissue shift away and create this underlying void. The other thing you'll recognize is that between the image on the left, which was low bandwidth, and the image on the right, which is high bandwidth, which is noisier? Which image is noisier, left or right? Right. This is definitely a noisier image. There's different places you can pick up on that, but if you look at the muscles behind the knee, you can see that this is a very splotchy sort of signal, and this is relatively smooth. And that should make sense to us that high bandwidth, it was in the denominator rather of that square root of time term. So high bandwidth images tend to be noisier. They have less chemical shift, so that's good. But everything's a trade-off in MR, right? So less chemical shift, but noisier images. So clinically, you have to find what's the trade-off that's acceptable. So this I think we saw. Okay, so interestingly, individual pixels are usually going to be a mixture of fat and water, right? It's not, our bodies aren't that discretely organized, right? So you're going to have areas that are a mix of fat and water. And the pixel intensity is just the sum of whatever fat is doing and whatever water is doing. And depending on the pulse sequence, depending on whether it's T1 weighted or T2 weighted or proton density, the signal from fat and the signal from the other tissue will have different magnitudes, but they just add together inside that pixel. But remember, they also have different frequencies, right? So here we have a pixel, and let's say it's half fat on the left and it's half water on the right. And those things are going to process, but they're going to be processing at different frequencies. So I've excited them, they're in the transverse plane, and they process. And the point at which I acquire my imaging information, let's say they're back in phase like this. If I add those two things together, right, I have a bulk magnetization vector that's pointing in this direction for fat, and a bulk magnetization vector that's pointing in this direction for water. If I add those two things together, those spins in this case are in phase, right? The bulk magnetization. They processed at different frequencies, but they ended up eventually pointing in the same place, right? If I add those two vectors together, I get something that's greater than 0. If I waited to a different point in time and these things were processing at slightly different frequencies until they were actually opposed in phase, one's pointing left, the other's pointing right, then the vector sum of those two bulk magnetization vectors is actually 0. So now something really interesting has happened, right? For this particular case, you have a water signal that's available, and you have a fat signal that's available, but because they're in opposite directions to each other, there's no net flux through your coil, and you effectively get no available bulk magnetization, no measurable bulk magnetization. And so if you time your imaging experiment for fat and water to be opposed in phase or out of phase with one another, you can cause pixels that are a mix of fat and water to be low in signal intensity. And that could be useful diagnostically. I'll show you another trick that we can play as well. So what controls the phase between those two things is the echo time, right? You excited the spins into the transverse plane. How long did you wait before acquiring your echo? And you can time this very precisely, right? We can control the clocks at microseconds, nanoseconds. So we can control the clocks on our acquisition system so that from the time we excite to when we actually acquire, things are either in phase with each other or we wait a different amount of time and now they're out of phase with each other. And just by changing the time at which we exactly acquire our signal, we'll get fat and water in phase or out of phase. It's pretty cool. So here's two gradient echo images, same imaging parameters. We've just changed the echo time slightly. And you don't really have to change it by very much. It has to change by, I forget what it is, but it's like 1.2 milliseconds or something like that. So on the left-hand side here, you have fat and water are in phase. And on the right-hand side here, you have fat and water are opposed phase or out of phase. And when you look at the opposed phase image, what usually stands out is you have these kind of streaky artifacts, right? You have these sort of bands of signal that appear to be sort of lost. And that's because within the domain of that pixel, there's a mix of fat and water. And because of your echo time, you've forced fat and water to be out of phase. And so their net vector sum is going to be very low. Might not be 0, but it's going to be lower than if they're in phase. And so you tend to get these kind of edgy looking images on the right-hand side, whereas the left-hand side, the in-phase images, things generally look a little bit smoother. So we can point out some different areas where we sort of see these effects. But the point is, diagnostically, this could be useful. You could separate out whether a compartment is a fatty compartment or a watery compartment by looking at what happens at the boundary of things. And usually fat is relatively benign, whereas watery things may be more tumor-like, and they may not stand out the same way in, say, the opposed phase image, as opposed to a fatty tumor that would really stand out in the opposed phase image. So let's look at some examples here. So we've got two images. These are just coronals through the head. So you can just be oriented. This is the spinal column, the neck. Here's your spinal cord, and then the brain, and your nose, and your tongue. And we've got two images. We've got one that's an in-phase image and one that's the opposed phase image. Again, the answer is probably in your slides. And to move quickly, I'll just point out some really discrete differences here. But you can see that in the opposed phase image on the right, you tend to get this sort of really kind of edgy and kind of streaky images where you can see really distinct differences between, say, watery tissues and sort of mixed phase tissues. So you get these really dark kind of bandy artifacts in the opposed phase image relative to the in-phase image. For a long time, this was sort of what clinicians would do. They'd look at the in-phase and the opposed phase image, and that would give them some insight about how, what a tissue was comprised of. Was it a watery tissue? Was it a fatty tissue? Was there a tissue boundary here that maybe wasn't apparent except for the opposed phase image? And now things are increasingly moving towards this. We typically want to differently visualize fat from water. We want to identify fat because fat typically is more benign than other things. And so we'd either like to suppress the signal from fat, or we'd like to reconstruct images that give us a water image and a fat image. Lots of different reasons that you might want to do that. Fat can also obscure underlying pathology, so you want to push the fat away so you can just focus on things that you might really care about. So let's talk about different ways that we can do that. One way is so-called fat suppression. And what you do, we know that fat and water precess at different Larmor frequencies. So we design an RF pulse where the carrier frequency of the RF pulse is really tuned pretty narrowly to fat and not to water. So if we have a perfectly homogeneous system, water's precessing at this frequency, fat's precessing at this frequency, I can design an RF pulse that only excites fat, ideally. It's not perfect, and that's part of the problem. So if you can design an RF pulse here that's what we call spectrally selective, you can tip down just the lipids, you can tip down just the fat signal, and then you can apply a spoiler. So you basically have an RF pulse that tips down fat, that spoils the fat signal, and then you go do a water imaging experiment. So the next thing you have is just a regular, say, alpha pulse for your gradient echo sequence, and then you play your slice select gradient, phase encoding, your readout gradient, and you acquire an echo. And this echo here should be largely a water echo because prior to that, you tipped only fat into the transverse plane and spoiled it. And so for at least a brief period of time, fat is relatively unavailable for imaging. The downside, of course, is that magnets aren't perfect, fields aren't perfect, RF pulses aren't perfect. Fat doesn't just process at a single frequency, but it's a spectrum of frequencies. So this works okay, but it doesn't work great. And when it doesn't work great, you get images that look something like this. So this is an image, that same slice that I was showing you before, that used a fat sat pulse in the spoiler to try to suppress the signals from fat. But if your system performance is mediocre, and oftentimes it actually is, you'll have some fat that doesn't get suppressed at all. You'll have other fat that gets pretty well suppressed. But overall, it's pretty hit or miss or heterogeneous. This is a bad example of fat sat kind of working. But it's not all that uncommon. So more interesting than just saturating a fat image is actually to generate independent, separate fat and water images. I think we probably have a group coming in next, so we'll go through this pretty quickly. But the idea is that with a particular echo time, I can acquire this echo for a gradient echo, and fat and water will have some phase between their two signals. Because they're processing at different frequencies, they have fundamentally slightly different phases. I can actually turn on another readout gradient, collect a second echo, but because the echo is even later, they'll have more phase between them. And I can do that a third time, say. So here, this is what we call a fast gradient echo sequence. I've acquired 1, 2, 3 echoes, and each of the echoes happens at different echo times. Echo time 1, echo time 2, echo time 3. And as a consequence of having later and later echoes, there's increasing amounts of phase between my first echo's fat water components and my last echo's fat water components. So now you get the idea maybe that I could separate out these signals. I could reconstruct a water image. I could reconstruct a fat image because I have multiple images that tell me something about the behavior of water and show that it's different than the behavior of fat. And so without going through all the steps, there is a way of using either linear or nonlinear approaches to reconstruct these different signals, these multiple signals, to give me a water image or to give me a fat image. And so the consequence is something like this. Now I can form an image here on the left-hand side, which is just the water image, or an image here on the right-hand side, which is just the fat image. I could composite those two images together to give me sort of the normal blended image, but this is the water image and just the fat image. So overall, we get imperfect fat saturation using that RF approach. We could look at in-phase and out-of-phase images, but they don't give us the conspicuity for bodies that are fat and bodies that are water, or regions that are fat and regions that are water. Whereas if we really reconstruct independent signals, we can get the independent water image and the independent fat image. And if you look at the fat image on the right, for example, like the whole brain and spine is gone because those are typically very fatty-like tissues at least. So really powerful technique. That's going to wrap us up for today. What was coming next was this protocol optimization for fast scanning. I would look through this. I think it'll give you some good sort of practical insights to how we actually design and put together protocols, starting with something that's pretty impractical and then changing the imaging parameter all the way down to be something that's pretty good. So I'd like you guys to look through those slides. I don't know that we'll have time to actually get to them. Okay, I know there's a group coming in next, so we'll leave it at that. I'll see you at lab tonight at 6 or a little like 7:15ish for that second group. And we'll try to get people through within, an hour plus of starting the lab. Okay? All right.